This is section 14.5, part B, and we just finished talking about the divergence of a vector field. We'll now talk about the curl of a vector field. Since the divergence was the del operator dot product with F, you probably aren't going to be too surprised to discover that the curl is the del operator cross product with F. Since cross product is only defined in 3 space, we'll start just by assuming that F is the vector field FGH. And that means our curl is going to be this del operator crossed with the vector field. Maybe you haven't done these by hand for a little while, so just a reminder that we have our I, j, and k vectors along the top row of our matrix. And then we'll have to put the del operator here in the second row. And then the third vector, or the second vector rather, FGH along the third. If I use my little trick to do this calculation, I'm going to end up with, let's see, partial h partial y times I plus partial f partial z times j plus partial g partial x times k, subtract this will be partial f partial y times k plus partial g partial z times I plus partial h partial x times j. Or if I collect the i's and then the j's and then the k's, for the i's I would have partial h partial y minus partial g partial z. J's are going to be partial f partial z minus partial h partial x. And the k's, partial g partial x minus partial f partial y. Now, rather than memorizing this, if I want to find a curl, I'll usually actually put this together and do my actual cross product. It tends to be easier than trying to remember that. But I do want to write this out for a specific reason. Quick little note here. What if the curl of f turns out to be equal to 0? Well, if that's true, then each component would have to be equal to 0. So if this component, and maybe I'll just go ahead and write these with their abbreviated forms here. There we go. If this is 0, then h sub y would have to equal g sub z. And if the second component is 0, f sub z has to equal h sub x. And if the third one is 0, g sub x has to equal f sub y. If you feel like you've seen that set of 3 conditions before, you have. Way back when we were talking about what made a vector field conservative, the 3 conditions that we just found are exactly the 3 conditions that we had listed here in order for a 3-dimensional f to be conservative. So, if we generalize, we can now say that if the curl of f is equal to 0, then f is conservative. And you remember in the last section, we said that there was another word we sometimes use. We sometimes called it irrotational. It's the same condition, just different words for them. If we do have a conservative vector field, so curl of 0 gives us conservative, we also know that the circulation is equal to 0 on a closed path C. So again, some of these things starting to hopefully kind of come together. All right, let's look at a couple of examples of calculating curl. We'll start with this radial vector field. Since curl has something to do with rotation, and the radial vector field doesn't rotate at all, I'm kind of expecting this one to turn out to be 0, but let's find out. The curl of f is the del operator cross product with my vector field xyz which is going to give me 0 here, 0 there, and 0 here, right? In every case, we're taking the derivative of something with respect to a different variable. So all of these are just going to give me 0. Minus and again, same idea. X with respect to y is 0, y with respect to z is 0, z with respect to x is 0. So, not real surprised, I do indeed end up with 0 for the curl. Technically, it's the 0 vector, 0i, 0j, 0k, meaning that my vector field is conservative, or we'll now tend to use the word irrotational. All right, let's try this other one. New vector field here. So to get the curl of f, we once again take our del operator, cross product with this vector field. And so I'm going to set up my matrix. And first of all, I'm going to get, let's see, there's no y's here, so that'll be a 0i. There's a z there, so a negative 2zj. And then that's just the derivative of a constant, so 0k. Minus, going the other way, no y's here, so 0k, plus the derivative of a constant, so 0I. And with respect to x, I'm going to get a 2zj. So I end up with negative 2zj subtract 2zj, or negative 4zj for my curl. So this time f is not irrotational. I did not get 0 for my curl. All right, I'd like to look at this again just a little bit with respect to the geometry to help you get a feel for what exactly do we mean by curl. And so I went ahead this time and I printed some things out from Maple so that I can draw on them and we can talk a little bit about them. All right, first of all, here's the actual Maple document, but then again, I am going to transition over to the printed copies in just a minute. What's nice about the actual Maple document is you can see it in color, which helps us to see a little bit more of the depth. This first field, plot 3D, is the vector field xyz, the radial field, and here it is. You can see, just as expected, all of the vectors are coming out from the origin. And if you imagine this, there really is no rotation. Again, if you imagined it as like a velocity field, the source is at the origin, and you've got material being pushed out away from the origin at all times. So there's no rotation, the curl is 0. This is an irrotational vector field, but it would have a positive divergence. Everything's getting pushed out away from the origin. The second one, the one we just finished working with, here's this field plot 3D here. We've got x squared minus z squared, 1, and 2xz. So let's see if I can show you that one. There it is. And you can see here, if I rotate that a little bit, that you definitely have things rotating around here. This is not just going straight out from a single point. So this is not irrotational. All right, I'm going to go to the printed copy of this. Keep in mind what this looked like, because my printed copy, because it's in black and white, it's just a little bit harder to see the depth that's going on. But certainly we can see the swirl here that's happening. We can see the rotation. All right, so just a quick reminder before we look at the printout. Our curl was negative 4zj, j, the axis, the y-axis vector, right? Keep that in mind. So here's that same three-dimensional graph that I just showed you on Maple. Again, I know it's a little harder to see it when the color's not there, but we definitely saw that there was that rotation or swirl happening. What I did with that graph is I just rotated the graph around until I was looking straight down the z-axis. That's what you're seeing here. Okay. This is the x-axis, this is the y-axis, the z-axis would be coming straight up from the page, which is why you don't see it. It's like you're looking straight down on top of it. Notice that we're not seeing rotation. There's no rotation around the z-axis. The vectors all just seem to be going sort of one directional. The same thing occurs if I look straight down the x-axis. Again, I rotated my Maple graph until I could see the y-z plane as though I'm looking straight at it. The x-axis would be coming out of the paper here. Once again, the rotation has disappeared. All my vectors just look like they're in a single direction or straight lines. Now look what happens if I look down the y-axis. I made this one bigger. Here I've rotated my Maple graph until I'm looking straight down the y-axis. So here's the x-axis and the z-axis. Y is coming up vertically towards you. Now we see the rotation, right? Now you're seeing that swirl, the rotation of the vectors. As a matter of fact, I can even go a little bit more than this. Notice here for positive z values, the rotations are basically in the clockwise direction, right over here as well. Rotations are in the clockwise direction. Clockwise direction is the negative direction, right? So for positive z values, rotation is clockwise or in the negative direction. Down here, for negative z values, I have exactly the opposite. Look which way the arrows are going. We're going this way. We're going this way. Now, for z less than 0, our rotation is counterclockwise. Counterclockwise is what we generally speaking think of as the positive direction. How does that fit with our calculated curl? Well, notice, if z is a positive number, the curl ends up being negative because of the multiplier. So when z is positive, curl turns out negative. It measures that negative rotation. If z is negative, negative times negative would be positive, and that's what I have down here for negative z values, a counterclockwise or positive rotation. So once again, we can kind of correlate some of what we're seeing geometrically with the calculation that we made for the curl. All right, to finish out this section, I'd like to bring all the pieces of divergence, curl, and Green's theorem together. I want to start by reminding you, when we did Green's theorem in the circulation form, we said that the integrand here was actually the two-dimensional curl. And when we did Green's theorem in the flux form, we said this integrand was actually the two-dimensional divergence. I've rewritten Green's theorem here just to emphasize that the circulation f dot TDS can be calculated as the double integral of the curl, and the flux, integral of f dot NDS, is the double integral of the divergence. Let's think about this now in terms of the geometry and the understanding of curl and divergence that we've been developing. We'll start with circulation. This said that the circulation, something that's happening out here on the boundary, could be predicted by something that's happening inside of R. Well, what was curl again? Curl was measuring how much rotation we were getting out of our vector field. So, if you've got a lot of rotation inside R, that's going to cause circulation to happen on the boundary. It's kind of like, in the old days when you would walk around and around inside of a pool to create a whirlpool. That's the same effect, right? We're creating the whirlpool in here with the curl, and that's causing around the edges this circulation to happen. So the fact that those two are related is not surprising. Now what about flux? Flux, the integral f dot NDS, was a measure of how much stuff is crossing that boundary. We said before that that was the double integral of the divergence of f. Well, again, what was divergence? It was a measure of how fast a vector field is expanding or contracting. So if inside of R, we have a vector field that's expanding, if that vector field expands, it's going to push stuff out across the boundary, and you're going to end up with a large and positive flux. If the divergence is negative and your vector field is contracting, you're going to be bringing things in from across, and you'll have a negative flux. So the fact that divergence is related to flux also should not be surprising. All right, that brings us to the end of section 14.5.